Okay, I know it's a lot, but hear me out. I bought a couple 3D printers for some hobby projects, and while things were spiraling out of control over the last several episodes, in this video things will start coming together. If there's a better metaphor than a vortex of chaos known as a tornado, I couldn't find it. That's right, I designed and 3D printed a helicopter from scratch. Crazy, right? Well, maybe not. Let's get into it. Way back over 20 years ago, when I was in college, I worked as a research assistant at the University of Maryland Rotorcraft Center. Mostly that meant machining parts for ongoing apparatus to help grad students accelerate their research efforts. We worked frequently with coaxial rotor systems. The Martian Autonomous Research Vehicle, or MARV, was born in our lab. This early research was a pathfinder to what eventually evolved into Ingenuity, or Ginny as we call her. Humanity's first powered flight on another planet was an especially proud moment for me. In recent years, 3D printing technology has advanced to the point where just about anything can be printed on a common FDM printer. I aim to test this premise by using a Bamboo X1 printer to make all of the functional parts of a coaxial helicopter and use this to visualize the flow through this complex system. In my previous video where I failed at lasers, I learned how to use laser light to illuminate a plane to begin to understand how fluids move through space in special circumstances. Now we'll use the same technique to understand flow through helicopter rotors. And we'll get really into the weeds here. I have said before, don't print bearings, but I printed the bearings in this design. I also printed the shafts and the gears and the airfoils and all of the brackets and clamps to hold everything together. Pretty much the only things not printed are the nuts and bolts keeping everything together. There's also some carbon fiber and steel in the blades because of the realities of aerodynamic stability. More on that later. I even considered printing the motors, but given my previous failure with mechatronics, I decided to use boring off-the-shelf motors and electronics. Maybe something we can revisit in a future version. Before we move on, there's a key aspect of 3D printed bearings that I wanted to highlight. I've thrown a lot of shade, but they're actually really viable. By using a specific configuration of roller bearings, we can achieve a bearing capable of supporting loads in both radial and axial directions. The key is to make the rollers just a little shorter than their diameter, maybe 0.2 to 0.4 millimeters. This allows space for the orthogonal rollers to sit smoothly on races without binding on their rotation axis. Shout out to Robert Murray Smith, who has also championed this bearing style. I've published a parametric model to make it easier for anyone to print their own bearing in any size they need. Onshape is a free CAD tool. They're not sponsoring, but it is my daily driver for 3D modeling. You can find the bearing model along with all the models used for this project freely available at the links in the description, as well as affiliate links for the parts I bought from Amazon. The gearbox uses double helical gears to reduce the motor input shaft speed down to a range suitable for our experiments. I chose the gearing based on a combination of factors. The motors I have on hand max out at 5,000 RPM. The camera I plan to use to record footage can film up to 960 FPS. I want to time the rotor with the camera such that the blade position is consistent in frame. This means I need to correlate the camera frame rate with the blade rotation rate. As a natural consequence, we have some convenient quantum levels to work with. In other words, as long as the camera frame rate is an even multiple of the rotor speed, this should work. Conversely, as we speed up the rotors, we run the risk of slinging their contents radially outward with reckless abandon. I don't want to break anything in my house, nor impale myself or my neighbors for science. So we keep the speed below 250 RPM. This means if we run the rotors at full speed, we need a 20-to-1 ratio in the gearbox to achieve this at full power. We don't need full power though, so throttling the motors to 3-to-1 ratio will have to do. I originally designed 5-1, but the set screws caused the gears to bind. Whoops. A few quick words about the rotor hub designs. The blades fit into a clamp at the root and have several set screws to hold things together. These clamps are connected to the hubs by pivot screws to allow the blades a degree of freedom in plane. The blades themselves are designed specifically to move their center of mass forward of the center of pressure. This is achieved by inserting steel rods in the leading edge. There is also a carbon fiber rod located at the center of mass. This is the rotational pivot relative to the hub and would act as a pitching axis if articulation were in play. This specific airfoil has its geometric center of pressure at about 35% of the chord, so we locate the center of mass by convention at quarter chord. If we do not locate the center of mass forward of the center of pressure, the blades experience aerodynamic instability. This can also happen if the local angle of attack exceeds the stall angle for the blade. Above the stall angle, the blade experiences chaotic aerodynamics, which will most likely rip the rotor apart spectacularly. There is also a potential for catastrophic failure mode known as flutter, where the bending of airfoil surfaces causes aerodynamic instability. Pretty much all of that is bad, and we want to avoid it. So, we've covered all the gearing concerns and key aspects of helicopter aerodynamics. Adding in some wiring and motor controllers, we can control the speed of each rotor independently. We have some confidence the blades won't fly apart. But do we really have confidence? Before we run the tests at speed, we need some evidence it won't fly apart. We need to make sure the blades and hubs will survive the severe centrifugal loading of their designed operational conditions before we can go slinging them around at great speed. But for that, you're going to have to wait for part 2, where I dive into more detail about blade construction and pre-flight testing. Until then, remember, when mistakes are welcome, growth is guaranteed.